Welcome, everyone. I'm Tracy Fitzpatrick, and I'll be your moderator today. Thank you so much for joining us here at Netcom Learning, a market leader in promoting lifelong learning, training, and talent development solutions. Hello, everyone, and welcome to today's session, Agentic AI on Vertex. Unlock self-learning AI with Vertex AI. Presenting today's topic is Francisco, a seasoned machine learning engineer with over 10 years of experience in cloud and AI solutions. He specializes in designing scalable, secure data and AI architectures across AWS, Google Cloud, and Azure, helping organizations turn data into real business impact. With strong expertise in data engineering, analytics, and production-ready AI system, he brings a practical multi-cloud perspective to enterprise AI innovation. Bear in mind that this is an overview of a very robust topic. We offer a collection of technical and business courses that can be tailored to your specific requirements. If you are interested in a further discussion, you can make an appointment with our learning consultants through our website at netcomlearning.com. Today's session is also being recorded, so you'll get free access to the recording in the next 24 hours via email. Netcom Learning helps customers build innovative learning organizations by achieving a smarter workforce, adapting to change, and driving growth. We do this with a broad catalog of offerings, developing customized learning plans, and our global delivery capabilities. Since 1998, we have been empowering organizations with our managed learning services to help them reach optimal performance results and address challenges. We do have 9 practice areas in which we specialize. They encompass people, process, and technology training. Today's presentation is from the Cloud Practice Area. Netcom Learning offers a comprehensive training portfolio of courses for the topic being covered today. Our upcoming classes include various trainings on the given courses. You can also access a variety of marketing assets, such as the free training and blogs, by clicking on the available event handout. These offerings can be found with a simple search on our website at netcomlearning.com. In this session, we'll explore how Agentic AI on Google Cloud Vertex AI enables systems that can reason, act, and continuously learn. We'll also look at how AI agents can automate workflows, make decisions, and improve over time using real data. Finally, we'll touch on how Vertex AI helps organizations build more autonomous, adaptive, and self-learning AI systems for the future of intelligent automation. Now I would like to give you a quick overview of the logistics before we get started. To begin with, you do have the option to view in full screen by clicking on the full screen button on the right side of the GoToWebinar viewer. Simply hit the escape key to exit the full screen. Everyone has been muted except for our presenters. Feel free to submit any questions you have for the presenters here in the questions pane, and we will address them at the end of the session. And to get the best out of today's events, we've included the slides, courses we talk about, and marketing assets in the handout section of your GoToWebinar viewer. You may refer to them at any time to get a better understanding of today's topic. And we do realize that some of you may have to leave early and want to let you know that as you do leave the session today, you will be presented with a short survey. We would like to request for you to take a quick moment to participate in that survey. Your feedback really helps us understand your learning experience and improve our future sessions for you. The survey answers are measured on a scale of 1 to 5, 5 representing outstanding and 1 representing poor. And now I'd like to pass this over to our trainer to present today's topic. Hey, Francisco. Thank you so much for joining us today.
Thank you, Pressy. Welcome, everybody, to our session on Agentic AI on Vertex AI. This session, we're going to learn how to build, deploy, and scale AI agents using the Vertex AI platform on Google Cloud. Now, as a little bit of a warning, this platform actually went through a name change a little earlier this week. It is now called the Agent platform, but that is still Vertex AI. So it's all Vertex AI at the end of the day. Now, my name is Francisco Quintana. I am a Google Cloud AI trainer. I am certified in Google Cloud machine learning engineering, data engineering, and solutions architecture. And I'm also a Google Cloud authorized trainer who helped put together some of the Google Skills Boost content that you could take on the Google Cloud page. My aim today is to get you to use Google Cloud to build agentic AIs using Vertex AI. And again, just a reminder that Vertex AI is now called the Agent platform. This change was done recently, so maybe that's one reason why the content is slightly different. So what are we going to cover in today's agenda? Well, we are going to cover the fundamentals of agentic AI. We're also going to see Vertex AI's capabilities for building agents, designing autonomous AI systems. So what we mean by this is we mean systems that can make decisions on their own with minimal user input. We're going to look at some real world use cases. We're also going to learn how to scale our systems securely and efficiently and integrate agents into our workflows to help us accomplish tasks. We will also be looking at governance, safety, and performance in the AI space. Now let's get started with our first module of the day, which is the fundamentals of agentic AI. So a lot of times we're getting confused to a certain extent. What is agentic AI? We struggle to differentiate them between LLMs, between other tools, but really agentic AI is AI agents that can use third-party tools or internal tools they created to perform tasks. So let's start by looking at what traditional AI meant. I don't really enjoy using the word traditional, but here we're talking about models that were aimed to perform very narrow tasks. So for example, you could have a model that could forecast future sales, a model that could maybe generate new content, but it couldn't do much more than whatever it was tasked to do. Hence why we use the word narrow focus. Also, these models had no memory or state, meaning that they behaved based on the current information they had available. It was very difficult in the past for models to be able to refer to recent behavior or even historical behavior to help it make a decision. Obviously, this has changed quite a bit over the last few years. Another element of traditional AI was the human in the loop, meaning that oftentimes models could not execute without a human being making those decisions and influencing the outputs. And then, of course, they had static knowledge, meaning that their knowledge databases were not refreshed instantaneously. They were only trained on a certain amount of data that covered certain time periods, and they struggled to adapt. In the world of agentic AI, this is no longer the case. So, what is agentic AI exactly? Well, the definition I like to use here is that it's a system that perceives its environment, makes decision, takes action, learns while pursuing autonomous goals. So, what we're trying to say here is that this artificial intelligence can take a look at the current situation it's in, ask itself, do I need more information or more knowledge to perform the next tasks? And then it can potentially make those tasks. And instead of having humans influence its outputs, what it will do is that it'll have a reasonable set of instructions that it needs to behave within and then perform those outputs. So what are the common elements of a agentic AI system? Well, one is perception. Perception in this case is how can it take a look at the current task it's faced to do and what other signals or data can it use to solve this task? Oftentimes with historical models, traditional models, it could only use the information that it had been trained on. But now we can get it to read new data via the form of PDFs or APIs, look at documents, and even other external factors such as signals like outside temperature, maybe outside social media noise, and add those. Another element is reasoning. Previously, traditional AI, you asked it to do a task, forecast sales. But what happens if you said, don't forecast sales anymore, forecast churn rate? Still at the core, it's the same task. You're doing a forecasting problem on a numerical element, but it cannot solve it. But now with reasoning capabilities, it can say, okay, I haven't been trained to forecast churn, but I can work through the steps that you taught me to learn how to forecast churn in a near real-time environment. Next one we have is action, where it's actually able to assist itself by executing code, calling APIs and such. What do I mean by this? Well, let's assume I'm trying to get an agentic AI system to forecast future sales of oil. Maybe it needs to check what is the latest news about global events. And you'll use that by calling an external news API to extract that information. This is what we mean by using external tools or taking actions. It's going to actually use other information that it can trigger or action and execute it. It doesn't always have to be information. It can also action the creation of a new model or the creation of another agentic AI system, or even open up a dashboard. Next we have is memory. What memory does is that it actually helps the model understand the context. Traditional AI usually solve the problem at hand with the information that it has at hand. But memory could say, hey, I tried to solve this problem before, and I went through this decision-making process and it worked. So let me try to repeat this decision-making process. You see this a lot now in chat agents, that it remembers conversations that you had recently or even a few days ago because it stayed in the memory. Next we have is learning. How does it improve? We know models need data to learn, but you just can't throw data at a model and hope that it performs well. What you actually have to do is make sure that model can learn and teach itself how to act in this data. A good example of this is gaming engines with reinforcement learning. That's assuming the gaming engine is trying to beat the human player. The human player is successful, so the agent is learning what worked well and what didn't and play off that. And finally, we have orchestration. Orchestration is when the model can trigger other agents, or it can actually trigger other tools or functions to help it complete its task. Quite often in agentic AI, we're never going to have just one agent. We're very likely going to have some sort of leader or signal agent or parent agent that will instruct the other models to behave. So this is agentic AI. Now let's talk about agentic AI versus traditional AI. Side-by-side comparison. How does a traditional AI method handle goal setting? Well, the goals are fixed at the training stage and at deployment. It can't make too many changes after that. Agentic can shift to adjust to new goals at runtime. What about decision making? How does a traditional AI system perform a decision? Well, it makes a prediction or inference, meaning that it will perform one action, and out of that action, it will give you the result. Agentic AI is different. It can go through multi-step planning and reasoning. It can say, okay, to perform this action or decision, I need to go through this series of steps. Could be go step 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then execute those steps on each decision it makes. Not only does it can perform multi-step planning, but it can also do reasoning. It can refer to previous attempts or user feedback in near real time. If the user says, this is not a good answer or not a great result, it can say, okay, what about this result didn't seem good? And then apply that reasoning to fix it. Next, we have tool use. A traditional AI system is trained to solve a problem. Effectively, oftentimes it is really just a tool. And it can only output a certain result. It cannot use any external tools to help. Agentic AI, however, has access to whatever tools you allow it access to. So it could execute a web search. It could execute code that it writes on the spot. It could connect to external APIs if you gave it permission to. So agentic AI now can use more than just the trained data it was given to solve the problem. Next, we have memory. Generally, traditional AI models are stateless. Now, you can make an argument this is not always true, particularly if you're building a model with long-term, short-term history. But generally, they do not really have a memory system. Agentic AI does. So let's assume I trained a model to forecast a problem. And then yesterday, I wrote a message and I said, actually, this new variable is you need to take into account. I haven't trained the model. I just wrote a message to let it know that it needs to take into account the new variable. So this way, the model can now use that new variable with its predictions in decision making because it can remember the previous information I gave. And so now it's to be user-based information. It can maybe previously remember an API call that it made, and that API call came with a certain amount of information. Next, we have adaptation. How does a traditional AI model adapt? Well, it actually requires a retraining process. A traditional AI model needs to be retrained. This actually can be a little bit challenging because it has to be retrained, and that takes time and computational costs and potentially even financial costs as well. An agentic AI system doesn't need to be retrained every time it needs to be adapted. It can self-correct in real time through feedback loop systems. So this is a key difference because traditional AI, there's always the element of debugging, finding problems, and retraining. Agentic AI is a question of finding problems and applying the solution in real time or near real time. Next, we have human oversight. A traditional AI system cannot train itself. It requires a human to provide it the data. It provides a human to trigger the retraining process. It requires a human to let it know how long it can train for. Agentic AI systems are a little bit different. They can actually trigger the training themselves. They can self-correct themselves. They can debug themselves. So this way, the human in the loop is no longer really required. It just requires having a single element that it can train on or it can loop on. So what we're saying here is that you give it the restrictions and it would work perfectly. Now, let's discuss the final element, task complexity. What is task complexity? Well, it really comes down to how complicated can the task be for the model to solve it. Again, traditional systems have single defined tasks. At most, they'll have maybe two tasks, but generally very limited tasks. Why? Because they're supposed to be very, very good at one type of problem. Agentic AI systems can handle multiple problems. Just like earlier I said that an agent can be trained on sales and still figure out how to do churn rate predictions because it's able to apply those steps to it. So now you can see, particularly with large language models, that it doesn't just do one thing, it does several things. So this is the difference between agentic AI and traditional AI side by side. So now let's discuss how these agents actually learn and approach problems. There's actually quite a number of ways that it can do this. One method is the agent in the loop or the react pattern. What this pattern does is it observes, reasons, and acts. So what do I mean by this? Well, first, let's assume I give it the problem and I say, I want you to predict sales for me, right? So it's observing my input and it looks at what tools it has. Let's assume it has access to a ARIMA function that can do a time series forecast. Now, what was my prompt? My prompt was, I want you to predict sales for me. What's the model going to think first? Well, for how long? What's its next action going to be? Clarify the request. Reflect if this is a good request. So the model will come back to me and say, how long are you looking for your sales prediction to be? I reply, oh, yes, great question. 10 days. Now what happens next? The model observes, says, can I run a prediction for 10 days? Let's assume it can. Then it will start to run that prediction using its prediction engine. And then it will start to return the results of the prediction, and I would reflect on it. Now I give a feedback saying this is a good prediction, this is a bad prediction, this could be better, right? So now let's actually go back one step. What if I gave it a different type of problem? What if I told it I need to get all the information about a particular subject, let's say quantum computing? So what does the model do? Observes the task. Does it have tools? Let's assume it has an ability to do an open internet search to get the latest information on quantum computing. Then it's going to think about, how do I get the latest information on quantum computing? Well, I got to open up this tool. I got to download it. I got to organize it, and I got to report back. How do I do this? Well, I got to call this tool. Okay, can I call this tool by itself? Or do I need something else? Well, if I'm going to collect the data in a web search, it's probably going to come back to me giving me HTML code. So I'm going to need some sort of HTML parser to convert this into human readable. So that means another tool. Then it will reflect on those actions, and depending on how you designed it, it can either check with you if that is the correct approach, or it can just execute itself and then show you the results to see if it makes sense. So what you're seeing here is a observe, reason, and act approach, which we call the react pattern. And the purpose of this pattern is to give the model an opportunity to to observe, think, act, and reflect. And generally, just like human beings, when we take our time to really think about a problem, observe the situation, act on it, and reflect if this is a proper action, we get better results. Now let's go into the core components of what makes an AI agent. So far, what we've been discussing are the differences between traditional and AI models. But now we want to discuss what really makes an AI agent. Well, at the core, you need to have a large language model. Examples could be Gemini, Gemini Ultra, Claude, Opus, Claude Sonnet, and many more. What is the point of this LLM agent? The point is, it is the brain. It is the one that's going to interpret the code, decompose tasks, and make the decisions. Now, it might not be able to carry out the actions, but it's going to do the thinking for us. It is the brain. Then we have the tool layer. The tool layer is, what can it do? Can it do a web search? That's a tool. Can it download an API? That's a tool. Can it parse HTML? That's a tool. Can it create a graph? That's a tool. So the tool layer is the skills or the products or the tools that we have built to the models to perform its task. Next, we have the memory module. The memory module in this case can be considered two elements. It could be one, short-term memory to remember the context that was in, and another one, it can be its long-term memory, which could be represented by RAG databases or other sort of databases. So what is the purpose of the memory module? Well, it's to provide a base of knowledge for historical processing and long-term processing and a short-term context window, so it understands what you're discussing. So for example, let's think I have an AI agent and I ask it, recommend me some restaurants in Paris. Then I ask it, now some museums. If it didn't have that short-term memory, it wouldn't know that I'm in Paris anymore. It would assume that it was check with me saying, well, for what city? But then that doesn't make sense. We just wasted the whole previous conversation. So that's what the short-term memory does. Now, what if I ask it something? I want you to tell me all the famous restaurants in Paris where famous celebrities have gone to and which ones are open. It's very unlikely this would be in the short-term memory. So it would need to go to its long-term memory storage. Could be in a database, could be through a web search, very likely it'll be in some sort of database, and then it will try to pull in that information. So this memory is not something it would have in short-term context. It would be in some sort of database it can access. But the short-term memory about my conversation about Paris would be there. So this is why the memory modules are important, because it helps it remember and helps it keep context of what we're discussing. Next, we have the orchestrator. What is the orchestrator? The orchestrator manages the process. So the orchestrator, if you will, it's the project manager that says, okay, what tools are we going to use now? How do I organize those tools? How do I get them to execute correctly and return back to me? It is the planner. In a way, it's related to the LLM core because it'll get its instructions from the LLM core, but rather than doing the thinking, it is the one that does the management, right? It takes the idea from the LLM core and it'll start to say, okay, now going to activate these tools, go through the authentication. What happens if the tool fails? How do I fix it? So that would be the orchestrator. Next, we have the grounding layer. What is the grounding layer? Well, it is a set of knowledge that allows it to refer to answers. So, for example, let's say I asked it the question, what restaurants in Paris famous celebrities went to? How do I know that my answer is correct? Well, the grounding layer will allow it to check its answer against some sort of approved data source. The grounding layer will now give the answer and will confirm if my model answer makes sense. Grounding layers are very important because they're the ones that help us keep the honesty of the model. So these 5 elements make up the core components of an AI agent. Generally, the ones that you absolutely need are the LLM core, the tool layer, and the memory module. The other 2, I wouldn't say are optional, but you could technically get an AI agent to work without them. So now let's talk about some basic types of AI agents. Start with the first one, simple and reflex. What do I mean by this? It's very simply an agent like a chatbot. You give it an input, it gives you an output. You ask it what you wrote, it will write. Next one is model-based. This one maintains an internal world model to handle partially observed environments. So what do I mean by this? This means that I have a model that is going to remember what we were discussing, but it's going to keep this all internal. It's not going to have access to external tools, and it will only really remember what we were discussing earlier. This one is just using whatever the model gave it to perform the task. Next, we have goal-based. Goal-based now gets a little bit more interesting. Goal-based is I give the model an objective, and the model will use everything within its power to reach that objective. Unlike model-based, that is really just giving you a response by looking at its internal memory, goal-based now might develop a reasoning pattern. So if I say, I want you to forecast me the sales of this particular product, it might go through a series of steps and check itself against those steps and say, okay, do these make sense? Does it work with my grounding layer? Am I getting legitimate responses? You give it a goal and it will do its best to achieve that goal versus just getting a back and forth response like simple reflex and model based. Next, we have utility based. This one optimizes for maximum utility and value across multiple competing objectives. So what do we mean by this? Well, let's go back to my forecasting example. I want to forecast sales. What is the true value of me forecasting sales? Essentially market planning, right? How do I ingest this information? Sure, the model can print me out a bunch of text, that works. What if it created a CSV for me? What if it created a graph? What if not only did it create a CSV for me in a graph, but it actually said, I actually think that you're going to have a worse month next month. Maybe you should cut back on costs. So here it's still giving you the same objective, forecasting sales, but it's trying to maximize the value it's giving you in that answer. Next, we have learning agents. Learning agents learn from your behavior and your responses. If you didn't like the response, it adjusts. It does this through something known as reinforcement learning. Reinforcement learning is when the model takes a reward or a penalty every time it gives an output. So if it does a good job, it wants to maximize the reward function. If it does a bad job, it wants to minimize the penalty function. So it will learn through experience. Just like a human being, the more you practice something, the better you get. And finally, we have multi-agents. This is now no longer just a single model. This is a collaboration of AI agents working together to achieve a task. Usually you have a parent agent, or the project manager, as I like to call it, that makes all the decisions, that leads the team, and then all the other modules that help it collaborate. They're usually smaller multi-agents with fewer tools, but overall they encompass more powerful agents. So let's think about this. What if I wanted to create a tool that created a marketing plan? Maybe I have an agent for my paid media strategy, I have an agent for my organic search strategy, an agent for my social media strategy, an agent for my budgeting, and they all work together to generate that output. So these are some of the basic types of agents that we have. Now, what is the agentic AI market inflection point? Well, agentic AI has been growing quite big. It's expected to hit 47 billion US by 2030. 72% of enterprises are experimenting with agents in 2025. Productivity gains are 10x. Reduction in operational costs are reported to be 40% lower. Now, why is this possible? Why are we suddenly seeing the explosion of artificial intelligence and now being allocated in almost every aspect of our business life? Well, one reason is foundational model quality. Large language models now, compared to how they were when they came out in 2022, are a lot smarter. They use step by step, they can use tools, and they have a lot more information in their system. Next, we have infrastructure maturity. Now we can deploy complex systems using cloud native agent frameworks, databases, and serverless execution. So rather than running everything on my personal machine or even a cluster of machines in my office space, I can run it on the cloud, making it global. And what does the cloud give me? Near infinite computational resources. In fact, my only limitation is how much I'm willing to pay. So these would be some of the options we have now available to us. And it is more accessible, which now goes us to enterprise demand. Enterprises now need to work quickly. They need to analyze everything. I sometimes think about businesses that responded to the wrong social media message or forgot to check the price of one element, and then the business didn't exist or went through a tough period. We now need to process more data. We now need to perform more tasks. So there is a demand for automating knowledge work. If I gave you a 300 megabyte Excel file with 25 years of sales data, how long would it take you to read it, understand it, analyze it, present it? Probably a few days. Let's say 5. How long would it take an AI agent to read it, understand it, analyze it? Maybe not present it, maybe not gain insights from it, but those 3 earlier tasks, it can probably get done in 30 minutes or less. And now all that's missing is the human element. Next, we have cost reduction. One of the biggest challenges that we have is that we pay for a lot of tools. We have dashboard tools, we have data engineering tools, we have visualization tools, we have tools that manage day-to-day operations. Now with these agents, they can handle some of those tasks. So inferencing these predictions or tasks have dropped 90% since 2022. So you can run multiple agents economically because they're not as expensive as they used to be. And then you don't actually have to use a tool that you were paying X amount for locked into a 5-year contract. So Agentic AI is really starting to hit the market very clearly and is going to play a big impact in the rest of our careers. So we've talked about what Agentic AI can do. Now let's talk about the capabilities of building an Agentic AI system in Vertex AI. So what is Vertex AI? Vertex AI is a unified artificial intelligence development platform. It allows us to build, deploy, manage, and monitor AI agents at enterprise scale, all in one location. So rather than using multiple tools, We're now just using one tool, which would be Vertex AI. What does Vertex AI give us? Well, it gives us 150 open source models. These could be large language models. These could also be standard prediction engines, regression problems, recommendation systems. We don't have to train these models from scratch. We don't have to build them from scratch. We just connect and deploy. So our foundational models are not just Google-based ones either. We do have access to non-Google models such as Cloud Opus, Facebook's Llama, and GPT models. So great, we have a model. We know the model can do either a series of tasks or an LLM that's already been pre-trained. It still doesn't perform as an agent. So how do I build the agent? I got to add tools to it. It's kind of difficult to add tools, not easy. So what can I do? Well, Vertex AI has something known as the Agent Builder. The Agent Builder can help us use a simple to use user interface to build models. Excuse me, to build agents. So rather than having to write complex code and understanding frameworks like LangGraph, you can just do it. It's a nice and easy UI. Of course, if you are a passionate coder, you can also code your solution using Agent Builder SDKs. We talked about the importance of grounding. How does the model get information to make the right decision? Well, it's hard to sometimes get this information in one location. Sometimes it's not in one location. Sometimes it's in multiple locations you need to match. Google comes with grounding technologies like Vertex AI Search, which can perform Google search relatively easily. Not only does it perform a Google search, but it can also perform a search in different systems like movie catalog libraries, product recommendation systems, library books, and OpenAI sources. You can also develop your own RAG engines, or your better said, RAG databases. You can also use vector search, which is different than Vertex AI Search. Vector search allows us to search a database in a more efficient manner. And then, of course, you can connect to third-party connectors that are not inside the Google system, like Amazon S3 buckets, Azure Blob Storage, even external parties or external parties SQL database systems. So great, we have the foundational model, we built our agent, we've grounded it, we trust it. But can the world use it? How does the world deploy our agent? Well, Google Vertex AI can actually allow us to build AI endpoints that people can call externally. Now, what is the other benefit of it? It can actually help us build these AI endpoints at scale. If I'm getting very little traffic, then maybe I only run it on one cluster of machines. But through the power of Cloud Run and Google's JKE, which is Google Kubernetes Engine, it can actually scale to thousands of machines if it needed to. What if I didn't want to use machines? What if I wanted to use serverless? We have several serverless endpoints like Cloud Functions and App Engine. So we can now build our model and deploy it at scale with all the benefits and security of Google Cloud. But there's something else. We deploy a model in the open area. We need to manage it. How do we do this? Well, we have observability tools like CloudTrace, LLM model logs, safety filters, and RAG evaluation pipelines. So now let's jump a little bit more into the foundational model space. We have a series of Google-based foundational models. Currently, right now, I'm just going to talk about the Gemini system, but it's currently not the only system inside the Google foundational model space. We have Gemini Flash, which is a lightweight model built for speed and optimization. We have Gemini Pro, which is a more advanced model. It can do complex mathematical problems. We have Gemini Ultra, that is actually the ideal model for doing most reasoning tasks because it can go through a lot of complex steps. And Gemma Open, which is their open source model. Let's talk about these a little bit. Why use Flash? Well, Flash answers problems very quickly. For example, if I asked it, what's 2 plus 2? Flash would answer it right away. Gemini Pro will still answer it pretty quickly, but Gemini Pro might go through a few more thinking steps because it's a model that's trained to do multi-reasoning problems. So it will answer 2 plus 2, but it'll probably give you a longer explanation than you need. What about Gemini Ultra? Can it still give you 2 plus 2? Of course. But now it will give you a complete breakdown of each step that it did, each function that it did to calculate 2 plus 2. You don't really need functions to calculate 2 plus 2. It should be pretty standard, right? And then, of course, Gemma will behave pretty much like Flash 2.0 or Gemini 2.0, but it honestly depends on how you set it up internally and what access you gave it into your on-prem system. So this is Gemini family. Really important to understand about the Gemini family is that your models numbers will change. In fact, right now we're pushing closer to Gemini 3s and 4s, so you would have it, but they're still built the same in the core architecture. So now let's talk about how we can use these foundational models to build things. Well, we have Google Vertex Agent Builder. What if you're not a strong coding practitioner? Well, there's a no-code agent. It's a visual editor that allows us to design agent behaviors with drop-down boxes, like maybe I want a behavior to do a Google search, another behavior to create a Google slide. And I can just add those behaviors in drop-down boxes to create my agents. So you can build a reasonably well-performing agent without having to write a single line of code. But we still need to connect it to tools. Do I have to build a tool to connect to Google Cloud Storage? Do I have to build a tool to connect to Google Slides? Do I have to build a tool to connect to Google Search? No. There are, in fact, 40 plus native pre-built tools. So if you do need to access that data that requires a Google search, it is actually available already as a tool. Now, we talked a little earlier that probably one of the ideal formats of training a model is using multi-agents. Multi-agent orchestration can be difficult to do. You got to imagine all these agents will have tools, all these agents will have memory, all these agents will have different instructions. How hard is it to manage this? Quite a bit. But through Google Cloud's Vertex AI Agent Builder and the Agent SDK, you can orchestrate this using a user interface or a very robust and easy to understand framework to manage the agents. So you can create the parent-child relationships and know how to assign which tasks via which agent. Finally, we can add, sorry, not finally, we can add our conversation memory. As we discussed earlier, the importance of memory for these models. Now, how do you store this memory? Do you use a Google Cloud Storage? Do you use a solid state drive? Well, the beautiful thing about the Agent Builder is that it gives you several options of what's the best place to store memory. Perhaps chat history, storing it in storage is not ideal because it'll take too long to build up. Maybe it is ideal because maybe the chat history is too long and you can't store it locally in an SS solid state drive. It does give you the options to choose which one is better for you. So now that I've built my agent, I got to evaluate it. How do I evaluate it? Do I just prompt it, test it by myself? Do I hire a team of beta testers? Yeah, I could do that. And to a certain extent, I should. But I can perform Google's Gen AI built-in evaluation systems that will evaluate it across metrics that interest me. Maybe I care more about accuracy and text fluency. Maybe I care more about token output. Maybe I care more about latency. Maybe I care about all of them. So you can actually test it against these metrics by giving it scenarios of real-world problems they would have to solve. Then you need to deploy it. Oftentimes, when you deploy something, you need to save it in like a Docker image, host it somewhere, and launch it. Not with Google Cloud. Vertex AI gives you a one-click deployment option that makes this model accessible to the open public or to whoever you want by adding security elements. So that's a Vertex AI agent builder. Now let's talk about grounding in more detail. As we know, grounding allows us to make sure that the model can refer to itself against data, can refer to data to test itself, its accuracy. Google comes with different solutions like Vertex AI Search. Vertex AI Search is a pretty easy way of building a RAG database. You simply connect it to the source system, which could be a website, a PDF document, Google Cloud's BigQuery, which is their ideal SQL storage solution, Google Cloud Storage, or using your own custom semantic retrieval operation. This Vertex AI search base doesn't give you the full control of how the search would behave, but it gives you enough control that you're actually able to build a pretty reasonable response with it. Then we're actually going to go down one step and talk about RAG engine. RAG engine is essentially when we are connecting the model to a custom RAG engine or a RAG database. The RAG database will behave as our solution to collect the data. How is this different from Vertex AI Search? Well, in Vertex AI Search, I have a lot less control of how that model particularly behaves. In RAG Engine, I have a lot more control because I can set up RAG instances or conditions or metadata of how it should handle each particular prompt. I can give it instructions of how to filter through information easier. I can give it instructions of how to ignore certain information. It's essentially me building my own vector search versus vector AI search, which is already pre-built for me. And finally, we have data connectors. Again, not all our data is going to sit in the Google Cloud system. So we will need to rely on connectors like Firestore, SharePoint, Salesforce, Confluence, and Jira. This will immediately bring the data over to Google Cloud, where Vertex AI is hosted, and allow us to either store it in Vertex AI Search or RAG Engine. Then we have vector search. What is vector search? How is it different from vector AI search? Well, one, vector search allows us to build a vector database without using Vertex AI search. Vertex AI search is a Google product. Maybe we want to use a different vector database. For whatever reason, maybe we find it better. Maybe we get a great deal on that vector database. And we prefer to do it in this case. So vector search allows me to basically develop my own, sorry, not develop my own, but incorporate other non-Google Cloud technology. So now let's talk about our next step, which is connecting to tools. This is quite often the trickiest part because connecting to a tool requires authentication, permissions, instructions, calling that external tool, hence paying for it, and getting that information back, and then closing that connection. Well, the good news is a lot of the popular Google tools are already connected in Vertex AI Agent Builder. We have Google Search, Gmail, Calendar, Workspace, and Maps. So if it is a Google extension, very likely it's already there. But what if it's not a Google extension? Well, we can use the Open API tools to connect and build our own REST APIs. And then you just teach the agent how to call these APIs. Now let's talk about something else. What happens if the tool that I need is not built? What if it doesn't exist, right? Like what if it needs to write its own regression algorithm? Well, it can use code interpreter to execute code and also write code for itself. Quite often, a lot of people are using AI agents to help it write code. In this case, we're doing the same thing. We're using a code interpreter to write code that the agent can write, run, and execute, or to help you fix your own code. So I give an example how it can be sandboxed in Java and Python, just because it was a true popular language, but technically there are a lot of other languages like Ruby on Rails, Java, and C++, and I am also thinking of Node.js as well. So you can't, which I guess is JavaScript. So you do have your options. So we have our Google extensions, we have an OpenAI tools that we can write, we have our code interpreter, we can write code. What about data? Well, we actually have quite a bit of data. Those data tools can be easily connected to a model to feed our RAG systems or for the model to just call it directly without going to a RAG database. So there are already popular data tools that we can connect to. We can also create custom functions. These are functions that operate inside Google Cloud. They can be executed when we need to. And then, of course, we need to orchestrate everything using our workflow triggers. Workflow triggers allow us to execute the processes that model will go through to get to its final answer. So this is the tool calling element of Vertex AI and how we can use it to build our agents. Now let's talk about manage runtime. What do I mean by this? Well, this is essentially how we deploy the agents. How do we get them to the outside world? How do we make sure they're secure? How do we make sure they're scalable? And how do we make sure they're reliable? Well, the good thing about the Agent AI Builder and the Agent Engine, which deploys our agents from Agent AI Builder, is that it gives us session management so we can maintain life cycles of the machines. We can also switch between different compute powers, allowing us to auto scale and allowing us to build secure, reliable systems. Session management also takes care of solid state drives if you wanted to store your memory directly on the machine itself. And even if you deploy a new machine, it will still have that solid state drive. One of the great things about the Agent Engine is that it uses a distributed computing process to actually scale from 1,000 machines, sorry, from 0 to 1,000 machines on demand based on current usage. And you only pay for what you use. So what happens if you scale to 1,000 machines? Do you pay for those 1,000 machines the whole time? No. When you no longer need those 1,000, say traffic died down and you go back to 10 machines, you only pay for those 10. So you only pay for the 1,000 from when you use them. It's not like if you hit 1,000, you have to continue using. Now, of course, when we're developing our agents, we could want to use popular frameworks that are not native to Google, like LangChain and Llama Index. You could actually integrate these very easily into Google Cloud Agent Builder and Agent Engine. Both the Agent Engine and Agent Builder give us a way to monitor our performance of our model. One method is using the monitoring integration, which connects to Google Cloud Monitoring, to actually see token usage, error rates, tool metrics, and latency. Difference between Agent Engine and Agent Builder is Agent Builder is more about building a model, Agent Engine is more about launching a model, but both will have some sort of monitoring feature attached to them, which is usually done through Google Cloud Monitoring. Monitoring is extremely important to see the performance of the model, to also see if the model is performing well, but it's responding slow, and also to track tokens because customers pay for tokens. Next, we have creating virtual private networks, or VPCs, virtual private centers. What exactly is this part? Well, often we know that these models can behave in strange ways. We also know that people might try to prompt inject dangerous prompts into the model. So what do we do here? Well, a virtual private network allows us to create that model in a secure environment that no one can use, except the ones who have access to the secure environment. So even if you had that API endpoint, but you don't have access to secure environment, you will not be able to use the model. Now, of course, we need to deploy our models globally. Maybe we want to start in several regions. Maybe we want to scale. One of the great things about the Engine is that it allows near global scale. So pretty much all the major components on it are covered. I think just Antarctica is now covered. So you could deploy your agents multiple places worldwide or one global endpoint, but very likely you'll deploy it multiple places worldwide to make it easier for people to use. Now, one other element that's not really part about building a model, but something that Vertex AI gives us is the model guard. As I said earlier, we have 150 plus open source models. But it's not only open source models we have. We have specialized models that are native to just Google and partner models as well. So maybe we don't actually have access to change this model ourselves because partner models and specialized models sometimes don't give us that level of access, but we still can. And then, of course, we have all the Google first-party models available to us. Almost all the Google first-party models are easily accessible. Some do require special requests from Google, like the security models and the medical models. But overall, we can all use this. So now let's go into our next section, which is designing autonomous goal-driven AI systems. Why do we want autonomous goal-driven AI systems? So we want autonomous because we want the model to make decisions on its own without always requesting for human input. And why do we want goal-driven? Well, because we want the AI system itself to take a goal and do whatever it can to achieve it, rather than us giving it step-by-step instruction. So, what are the design principles of creating this goal-driven system? Well, I always say you want to start small. Give the agent one single defined purpose. I'm not saying task, I'm saying purpose. So if it is a slide builder or presentation builder, tell it that it needs to be a slide builder, presentation builder. If it is a forecasting agent, tell it it needs to become a forecasting agent. I'm not telling it what to forecast. I'm just saying that's going to be its purpose. Don't try to get it to do everything. Try to define one, maybe two elements to get it to do. Potentially, you can go to three or four. But again, they need to be related. You don't really want to just say you're an expert at everything. And just like any human, no one's an expert at anything. Another important design principle is fail fast and recover. Often these agents learn from experience, and sometimes the best teacher is failure. So you detect problems early, escalate gracefully, and never get stuck in infinite retries. If approach is not working, stop right there and try a different approach. Design these systems so they can be easily maintained, fixed, and adapted. Don't design the system that requires a monolithic change to get it working correctly. Next element is that we have minimal permissions. Minimal permissions essentially mean only allow the agent to use the absolute minimum tools necessary to complete the task. Don't give it more access than it needs. Generally, this is a good practice with AI. Always give the model exactly what it needs to complete the task, no more. If you think you might need to give it less, play it on the safe side and give it a little bit less. Because these models will use the tool to the full extent. And not to saying that they're going to do anything nefarious with it, but potentially the model could overuse your tool. So imagine if you're asking it to do a forecasting model and it needs to call an external API and says, oh, I want to get more data. And that data costs you money to get. Then you're overusing your tool. Next element, or design principle, sorry, is be observable by default. Every action or step that agent takes should leave a log. This helps us debug when it gets too far. Next, we always want to have a human to allow control the model if we feel that the agent is misbehaving or doing incorrect approaches. I always say that before I deploy an agent to production, it always requires a human to deploy it to production. I'm that last layer of testing. I'm that last check that needs to happen before the model goes live. So it's my responsibility to make sure that the model operates correctly before it goes live. So always give it an option for the human to review the last development of the model and such. Then deterministic core. Deterministic core basically means that the model needs to perform high-stake decisions, but don't make it go through make the agent go through a series of deterministic steps when it is a high-stake decision. So this is essentially like an if conditional where it'll go through these checks. This is also kind of your last kind of element of human before it goes, because you're the one who's writing those checks. And hopefully your model performs and passes all those checks correctly. Next, we have our architecture patterns. Here with the model architecture patterns, we're looking at things like how we build these models. So we talked a little bit about earlier how we combine the tools. Normally, you have one large language model with different tools. This is usually a good way of approaching it. Give one model access to different tools. The tools it needs to accomplish a task. Remember, keep it simple. If there are multi-agent systems, give those agents, those individual agents, the tools it needs to complete its task. Don't give it more tools than it needs or tools to a similar related model in your agent flow. Always make sure you have some sort of routing agent. The routing agent is the one that determines what is the next step of the process. For example, if you had an office agent builder that you have, that might need to communicate with human resources, finance, and IT. The routing agent will determine what is the user prompt and what is the next best location to go or sub-agent. Is it HR, finance, or IT? Next, you want to always make sure you have a sequential pipeline. Agent A output goes to agent B outputs. So what you want to do here is make sure that the model does not finish its answer until it goes through its entire agentic flow. The reason you have the agentic flow is to improve the model when there's an issue. So if you don't have it go through its entire agentic flow, it might give a bad answer before it got to where it needed to get to. So again, I highly recommend that you have the model go through all steps before it gets its final answer. Next, you want to take the approach of parallelism fanouts. This is when you have a coordinator that spawns multiple agents simultaneously. So what does this mean? Well, what if I want to simulate a little bit? What if I want to test various agents and see which one works better? I can have a multi-agent flow where it goes through all these series of steps. But next, maybe what I want to do is I want to run agentic flow A versus agentic flow B and see which one outperforms the other. This gives me a little bit more visibility and opportunity to add different tasks to to add the same task to different agents to see which one performs better. You could even have these agents compete against each other, which is an element of reinforcement learning. Now, remember that you always want a leader agent, a project manager agent, or a parent agent. The job of the parent agent is to break up the task for the sub agents, for the child agents. This is actually really important because remember, you don't want to give your specific task agents too much work to do or too complex tasks. So the parent agent should simplify it, almost like a parent whose job is to make life easier on their child. One of my favorite things to do is to use the debate approach. This is where you have both agents trying to complete the same task that communicate within each other or try to beat the other, saying, oh, I prefer agent A responsible over agent B. You need to do a better job. So this is actually a good way of tackling the solution. Let's take a quick 5-minute break, and then I'll start on the remaining topics after this break.
Sure, we are now going to take a 5-minute break, but before we do that, we are going to launch a quick poll that we want to invite you to participate in. Doing so helps us know how we can better serve you by telling us who might be interested in more information or in taking some additional training. In addition, we have a lot more informative webinars coming up, so please go to netcomlearning.com/webinars in order to register.
Welcome back, everyone. Let's continue from where we left off. Now, we've seen the architecture patterns. How do we provide the instructions to the model? Realistically, we use prompt engineering. This is essentially when we're going to pass instructions to the model by giving it the task it needs to do. However, we don't just simply pass the task. We give the model a identity. So what you see here is you see a system prompt structure. As you can see, we're defining the model identity. We're defining the scope of what it may or may not do, the tools it can use, the escalation, and the output format. This is an overly simplified example, but essentially it works this way. We always want to be clear what's the purpose, the goal, what it can and cannot do, what it can use and how to use it, such as you see, use query database for historical data, run Python for calculations, and escalation for saying when do you need to go to a human user or maybe not respond directly to sensitive topics. And of course, the final output format. So prompt engineering is a practice on its own. You could have essentially a whole course on it, but here is just a very simple example of how to prompt engineer. Now, let's talk about designing memory systems. Memory is key to the model, as we discussed. One way to handle this is by doing in-context memory. In-context memory means that it's going to look at the current conversation window. So you're passing as much information as you can within that context window. Now, this is really good for recent recalling and recent session reasoning, like very recent information. The problem with this approach is that you can't load up all historical data. It's impossible. You run out of space. Each model has a certain number of space in memory. We usually represent the space in the terms of tokens and usually pay for token. Now, Gemini models have a pretty large context window of 1 million to 2 million tokens, but the more tokens you use, the more you pay. So what is another way we can do this? Well, one way is that we can create the session storage, similar like a browser. We can use external storage systems like session storage that can be used with Redis or Firestore. And that means it keeps the context, but it can reset it. And it can also go back to other contexts within a similar session storage size. Remember, browser session storages are not meant to last forever, and they're also not that long-term, but they are more long-term than a extension context window. Next, we have long-term storage. Long-term storage is when we are actually connecting to relational databases or RAG systems. These are also known as vector stores. This is when we can give it an entire wealth of information, petabytes of data, libraries of data that it can refer to. This data is not in the model's short-term memory, but it's in the long-term memory, meaning the model will look it up. It's almost the equivalent of me giving you access to a library and I say, hey, I need you to look up when the Roman Empire fell. You might not remember it from memory, but you can go to the book in the library about the Roman Empire. It's the same concept. You're going to a certain section of your memory store to collect it, but it's not inside your current session. You don't currently remember. Next, we have structured or persistent storage. This is usually when we give the model access to like a SQL table, right? In Google Cloud, very likely you do this with BigQuery. Why do this? Why not just use vector stores? Well, quite often when we're trying to do numerical calculations, vector stores are not ideal. Main reason is because the data is actually vectorized locations versus actual numbers. Structured databases work often better. So this would be a really good one when you're trying to look at accounting data, policies that require numerical representation. Next, we have how to get the model to approach a problem. We already saw a little bit of the React framework, so we'll skip that. We're now going to think of chain of thought. What is chain of thought? Chain of thought is pretty simple. It is a step-by-step process. So for example, maybe I'm asking you to build me a wooden boat. You create a step-by-step process and you follow those instructions. Now what if I ask you to build me a wooden car? Well, pretty much you can follow most of those instructions, right? Tree of thought is similar. The difference with tree of thought is that we give it more than just one series of step-by-step instructions. We give it multiple sets of instructions that branch out. It's basically a decision tree. This is really good when you need to create open task or creative task, where you don't want to follow a rigid instruction, but you want to follow enough to expand. Next, we have React. We've already discussed React a little bit, but essentially it is observe, plan, react, and reflect. Next, we have plan and execute, a simpler version of the React framework, but simpler sometimes is better. What this one does is that it creates the plan, and it's not just step-by-step instructions, but it does take into account feedback loops, checks, and such, and it executes. The main difference between this one and React is that it's not going back to test, am I making the right decision? Or asking you for further input. Next, we have a strategy known as self-consistency. Self-consistency is when we run the same task multiple times and then take the majority answer. So what do I mean here with temperature greater than 0? Well, temperature impacts the model creativity. So what do? We test the same result. Sorry, we test the same problem multiple times with different levels of temperature and different levels of creativity. And then we take whichever seems to be the most common answer. Another strategy would be reflection. We give the model its own output and let it check it. So with reflection, we can apply any of the previous strategies. But at the end, we have to think about the problem and think about the answer before it gives it. It's almost like when I give you a test and I say, think about your answer before you hand it in. Well, now let's talk about multi-agent systems. As we discussed earlier, we need an orchestrator agent. So if I wanted an agent to help me perform a task, I would have an orchestrator agent go tell the other agents it needs. So let's assume I have one that is helping me write a financial report. I need to perform research. So if I say, write me a financial report on the current oil prices of 2026 and how it might have an impact on global trade. So a research agent is going to collect all the information. It's going to organize that information. It's going to pass it to the analysis agent. The orchestrator is the one that tells the research agent what it needs to do. And then it checks if the research agent has accomplished its task. This could be done with any of the strategies we saw a little bit earlier, and pass it to the analysis agent. Analysis will perform its analysis, check with the orchestrator if it's good enough, pass it to writing, and so on and so forth until we get to the very end. This approach is actually really nice when you have complex tasks. Writing a report on current oil price of 2026 and how can it impact the global economic trade is not a very easy task. In fact, you probably would have 3 or more people working on it. In this case, we have 5 autonomous agents that are sub-agents and 1 orchestrator, so a total of 6 that can handle this at extremely fast speeds. Next, we're going to talk about how we handle errors. Large language models will make errors. So our job is to make sure that we handle these errors gracefully, which is our first topic, graceful degradation. When a tool fails, the agent should fall back on a less than capable but reliable answer. So say, for example, that I use a tool that performs a search on financial data. In order to do that, I need to call an API, don't I? What happens if that API crashes? What happens if it's no longer available? What happens if I missed my limit window? Well, I got to go still get an answer. So there should be a fallback tool. Maybe it'll be an outdated table that we collected earlier. Maybe it's model memory. Maybe it's a Google OpenAI search, which is probably not the same level of accuracy as a API. Next, we needed to retry, right? But we want to retry with a backup. What do we mean by this? Well, we don't want it to continuously keep retrying. We want it to stop after a certain point. So we wanted to retry with certain conditions that are not infinite, but also not so rigid that it can't try different approaches. Another real big problem we have with errors is semantic error. What do we mean by this? Let's assume I ask the model to do a forecast for me on oil prices in 2026 and how they might be priced in 2027. What if I spell forecast wrong? What if I put 2016 and not 2027? What if I put 2226 and not 2027? This is where I made a semantic error. The great news is large language models are good at recovering, at fixing these things and noticing that there are spelling errors, grammatical errors, and things of that nature. So what is the best way to approach it? My personal recommendation is have a checker to check for spelling errors and fix it before it arrives. Next problem is that we hit a budget limit. What do we mean by max step budget limit? Well, often now you're seeing that large language models are charging you per reasoning steps. Each reasoning step represents a certain number of tokens. You might hit your limit of tokens or hit your limit of steps before it gets to its final answer. It's like me stopping you halfway through a problem. We need to be able to account for this. This means that we need to allocate before we start solving the problem a certain number of steps it can take. It might not be enough, but it's usually better to give an answer than no answer. And it's significantly better to give a answer than an error message. Sometimes we'll have agents that'll give partial results. Why? Well, generally it's because it could have hit a max limit on budget. It could have missed an API call, not gotten the full data, or maybe the response mechanism crashed partially. So if we do have partial results delivery, I often think it's better to not give the full result. You might want to give an error message saying, please retry again in a few minutes. Or you might want to give that partial result message, but let it know that there are some limitations or caveats. Next, you have human escalation triggers. This is when we define specific error codes, confidence thresholds, or tasks and automatically route the human reviewer to it. You see this often in chatbots when the chatbot doesn't know how to solve problems, so it goes to a human. This would be a good way of handling errors. If you feel that the model is not capable of answering the problem, you can then use a human in the loop to solve it. So now let's talk about some real-world enterprise use cases of these agentic AI systems. Let's start first by looking at the different areas agentic AI can touch. As we can imagine right now, there are actually vast areas that agentic AI can touch. We can look at financial services, retail and e-commerce, healthcare, manufacturing, technology, legal compliance, and more. 68% of Fortune 500 companies are testing agents. The ROI is 3.5% for your first year of investment in AI agents. 85% reduction in manual data entry and 60% faster customer resolution times. This is actually very interesting information because it's showing you how impactful these AI agents can be. So let's dive into a couple examples of these AI agents. Let's first look at financial services. In financial services, there are common agents that we can use. One of the most common ones that I've seen is research analyst agents. Why is a research analyst agent so common? Well, what's one of the main goals of financial service company is to research. It's to get that data and analyze it. This can take time, but an agent can do it in a few minutes. Next is compliance monitoring. I have yet to meet anybody that understands all the legal frameworks of any city, company, country. What can an agent do? Well, it can understand those regulatory rules very, very well. It can actually even tell you if you're in violation of those rules or potential violation of those rules. So it can actually make sure that you are legally compliant with all your tasks. Next, we have customer onboarding. Challenging. You need to get your customer on board in the process, validate documents, check credit history, and more. Often this takes some time, right? There's paperwork you have to fill, forms you have to check, human reviewers have to check those forms. But now an agent can do it a lot easier. It can check all those forms for you, and it can have a friendly conversation with somebody that is struggling to complete the forms, saving you human time. Next, you have risk assessment. Risk is one of the key elements of financial services. A lot of companies, such as hedge funds, rely on having strong risk assessment teams. So, how can an agent help here? Well, you've probably seen AI agents in fraud detection. So that's one risk that can be removed. I've often seen banks apply fraud detection to systems to make sure that there is no fraud taking place. And if there is, it's immediately alerted. Another one could be market risk. One of my favorite scenarios to do with AI is to get a opposite or contradictory AI. Let's assume I create a whole risk scenario. Makes sense. I would get my AI to tackle it and go against me. That way I can actually see if there's any errors in my report or maybe any risks that I have overseen. Next one can be trade settlements. Similar to compliance monitoring, but now what we're doing is that we're having the AI help us understand the intricacies of legal framework and contracts. Oftentimes the contracts take time to read, are difficult to understand, but with an AI, you can essentially simplify the understanding of it and make it easier to use. Healthcare is another big example of this. One of the most time consuming parts of healthcare is essentially helping the patients make decisions. They want to know when their lab results are coming in. They want to know the clinical guidelines, what they should bring, how to upload their patient history, maybe even check their own patient history. Obviously, this takes a lot of time for human beings to help out with all this. So you can have an agent that actually acts as a support system for that human patient. Another example in healthcare is making sure that you meet all requirements before attending the hospital or submitting your paperwork. How oftentimes have we seen delays in the medical field because prior authorization was not given? And what would be one reason for prior authorization not being given? Well, it was incorrectly filled and it wasn't delivered in time. So now you actually can have this done relatively easily by having the person upload the requirements and immediately detecting errors. After this, we could go to medical coding. It's not easy to understand what a doctor's saying to you. It's not easy for some doctors to be familiar with all the codes. So medical coding here can help patients understand ambiguous documentation in real time. So what are their information? What is the result of their treatment? This can make it simplified a lot easier. Oftentimes when I have done blood work and such, I don't even understand what half those words mean. Next one, which is actually very powerful and interesting, is drug discovery research. Maybe you've seen, but the Google Deep Brain team actually created an AI model called AlphaFold that actually was part of the reason members of the Google Brain team won the Nobel Prize for chemistry. Why? AlphaFold was able to come up with new protein synthesizing models that have never been done before in human history. This can be amazing for drug discovery research. Another challenge that we have is administrative tasks in the medical world, patient scheduling, resource constraints, appointment history, even support. So you can have an AI agent that can actually optimize your schedule, make adjustments, even respond to the human with delays and advice of what to do next. Next, we have IT operations steps. As we've seen, a lot of people are starting to rely on AI agents or programming and IT tasks. An AI agent can scan code faster than a human agent can and detect bugs. It can immediately respond to incident reports by closing down the system that has an error rather than waiting for the human to fix it. We have seen more people use AI coding agents. One of my favorite use cases of AI coding agents is using an agent to fix errors, potential errors in my code, especially security vulnerabilities. Remember, so a vulnerable security hole can be catastrophic to your business. In fact, it can even destroy your business if you're not careful. So it's often recommended that you use code review agents to at least help you find bugs in your code. And some people actually even use them to write their code as well. Next, we have an infrastructure optimizer. Every few days, there's a new technology out in the market that we need to use for our AIT solution. Well, what if we don't know how to use it? This is where an optimizer can help us. It can help us understand how to use this tool and how to apply it. Next, it can also help us understand how to improve cloud spend, which is usually surprisingly high cost, and also usage patterns to improve performance. We can also have active security threat hunters. I'm not sure if you saw, but you saw that Anthropic's model actually detected 500 zero days in enterprise level code for some companies. Just to give you an idea, if you have one 0 day vulnerability, that potentially could be worth millions of dollars. They found 500 zero days in programs that were quote unquote secure. This is vital to the industry. Next, one of the most difficult things in DevOps is to coordinate deployment schedules. An AI can help create a deployment pipeline, check for incorrect deployments, and send metrics to the user to help out with that. And probably one of the most popular use cases of AI is customer service. We've probably seen this to a great extent in day-to-day, where we're talking more and more to AI agents in customer service roles. One, they can help understand intent, fix typos, and look at millions of requests to compare in seconds. They can be integrated into CRM systems, billing systems, logistics systems, product systems. They can perform autonomous resolution, such as execute refunds, provide exchanges, account updates, escalations, and more. They also have sentiment-aware routing. What does this mean? This is actually really cool. Sentiment-aware routing is what can detect frustration, urgency, or VIP status in real time, and then escalate to a human. So essentially making sure that the customer is always right. Then we have quality assurance, where it can review all the customer agent interactions and make sure that there are no compliance issues or missed opportunities. And finally, it has knowledge self-service. It can look up its own database to read the latest documentation. Because as we know, humans are not going to remember everything, and it might take a long time to just review the documentation or ask somebody. Versus knowledge self-service, where it can actually look up the documentation itself in just a matter of minutes or seconds and give an answer. And finally, we have elements like legal compliance, where it can do contract analysis and flag any potential issues. It can process 200-page documents in under 2 minutes. It can also help with regulatory change management, see how policies might affect people, estimate how people will feel with these policies, and even give tips on how to slowly deploy these policies. It can obviously perform complex research in a matter of minutes, if not seconds. And it can help you maintain policy management, track version history anytime a document gets modified. And of course, it can also monitor third-party risk. So these are elements that maybe are not part of your original legal analysis that most recently came up. such as legal law changes or developing situations in the particular environment you're working in. So in all of these, we have seen them deployed. So which one currently is getting deployed at the highest level? Right now, I would say legal review. So legal review is actually being used quite a lot with AI. Realistically, in the research phase, lawyers are traditionally very good researchers, and they need to perform high-level research, quality research to usually win their cases. So now that we understand what are the impacts it can have on several industries, let's take a look at how we can scale these AI agents securely and efficiently. Well, the good news is scaling is relatively easy using Vertex AI. Now let's see why. One of the elements of scaling an agent is we got to think about computational scale, data scale, and organizational scale. Computational scale is how do we provide enough compute power for the agent to work correctly? One thing that we could do is stateless agent pods. This means that we create them in a Google Cloud container that is stateless, meaning that there is no single source hardware or specific I don't want to say the word specific, but limited hardware, saying you can only use 3 machines or such. We put it in a state that it can actually be deployed almost anywhere and horizontal scale out. Essentially use as much hardware as it needs. If it needs 10 machines, it'll get 10. Now, of course, in Vertex AI, you can put cost controls to make sure it doesn't go to 1,000 machines and then suddenly you get a massive build the next day. Next, we have async job queuing. What is async job queuing? Async job queuing is essentially when we're going to send the request to the agent, but manage it in a way that allows us to not have a crash of our system, a traffic, essentially a bounce, right? It's going to take all the tasks and it's going to manage them. And it's going to say, okay, I'm going to send these tasks in this order, maintaining the order history, maintaining the process without having the system crash. Next, it has a caching layer, could be good. Oftentimes, LLMs respond slowly. One of the biggest complaints I've seen in LLMs is how slow they run. So Vertex AI can actually deploy a caching layer for your memory store, which is a product in Vertex AI or a Redis database. And this memory store can actually reduce inference costs by 30 to 60% for repetitive queries. So someone had already asked that question. Should we go through an entire flow to answer it if we know the answer doesn't change? The answer is no. It can rely on memory store, which is a Google Cloud product, to go through that caching layer. Next, we have agent fleet management. As we discussed, we might have multiple agents. All of them will require computational resources. Google Cloud, through the GKE, which is Google Kubernetes Engine Autopilot, manages all these agents for us. Sometimes they'll give a certain agent 3 machines. Sometimes they'll give it 200 machines, depending on what it needs to complete the task. Next, we have regional failover. This is when a certain region has hit a load balancing issue. So maybe we used up all the computational resources we can in region A, so it can shift to region B. Maybe, God willing, no, a certain region crashes due to environmental problems. Should our model stop because of that? Ideally, no. So it could be deployed to a different region that has the capable liability. Then finally, we have cost governance. Cost governance is essentially when we are monitoring the cost, looking to optimize it as often as we can, and making sure we don't have massive bills coming to us at the end of the day. So these are some of the architecture patterns that we can use. You don't always have to use one. You can use all of them if you want to. Now let's go to our next topic, security architecture. This is actually probably, in my opinion, the most important. Why? The reason this one is very, very important is because this one actually is what makes sure that your agent doesn't get um, a security issue. Who can use your agent and how? That can be controlled through Google Cloud's Identity Access Management, or IAM. You can dedicate who can call that agent and use it. One of the most common ways to manipulate an agent, if you make it accessible to the public, is through prompt injections. This is when I put dangerous prompts inside our AI agents. Google Cloud has prompt injection defense systems through Model Armor to make sure that that agent does not get corrupted to dangerous prompts. It can also make sure that all tools require a permission and minimal permission they need. So for example, if we have a research agent, should it be able to create and delete tables in a database? No. So you can actually control permission saying this agent can only read from the database. Another option that we have is output sanitization. There are products in Google Cloud, such as DLP API, which protects against personal identifiable information, Model Armor, and Google Cloud's security service checks. Security service checks check for dangerous answers or dangerous inputs. In this case, we're talking about outputs, so answers. Maybe the model is giving an answer that could be harmful. So go through a security check, and if it fails the security check, it will not provide that answer and it'll just come back with a generic response. Maybe somebody asked the prompt saying, hey, show me everybody who registered for the service. We shouldn't be showing that. Or maybe the model made a mistake. However, the output sanitization tool through Model Armor or DLP API can check, hey, there's actually a PII violation in this answer. Let's hold off on it. Particularly if you're based in Europe, PII violations can cost tens of thousands of euros per violation. So suddenly your single violation becomes a massive violation and you will have a massive bill. Next, we have audit logging. Any system requires us understanding how to check the quality of our tool. So what do we do here? Well, in this scenario, what we do is that we output all our tools, including our agents and multi-agents, and how they're being used. And then we test if they're being used correctly. And we can log all those reports to manage them. If they are working correctly, we can continue as so on. If they have bugs, we can also continue as so on and fix those bugs as we continue. And finally, we have network isolation. This is a way to control who can access the model by creating a private network. It's almost like I'm creating a sandbox environment that this model can work and behave in. So now let's actually talk about cost optimization and how we can improve this in the Google Cloud space. Cost optimization can be done through model tiering, where we can actually route simpler tasks to the cheapest model, so we're not paying for the most expensive model to solve a common task. Another approach is through context compression, where we can summarize complex context windows or RAG databases into smaller amounts. Remember, we pay per token. The longer context window, the more tokens we use. Another option could be semantic caching, meaning that if the model has already answered a similar question earlier, it can actually just pull that answer rather than running the whole process, hence using tokens. Then we have batch processing. Batch processing is when the agent can actually put all requests into a single batch call rather than an inference real-time call. An inference real-time call is the model's going to answer everything immediately. A batch call, it can put all the prompts or tasks in one single call, which will be more cost-effective. Now, one of the great options we have for cost optimization is spot and preemptible instances. Spot instances in Google Cloud are virtual machines that allow us to power our agents that come at a 60 to 90% reduction in cost compared to a normal machine. Why does Google do this for us? Well, spot and preemptible instances are actually really cheap because Google reserves the rights to take them away if they're not being used. Now, I'll never take them away if they're currently being used. But let's say for right now, I use 3 non-spot instances. Now I'm getting a lot of traffic. I need to scale to 100. So Google gives me spot instances at a massive discount, 60 to 90%. But then I decide to not use them anymore, or my stateless pod decides not to use them anymore because it doesn't need to manage it. Right? We don't have that much traffic anymore. Google reduces me back to my 3. So I don't pay for all those 100 the whole time. It's a great way to maintain reliability and scalability at a low cost. And honestly, one of the best ways to maintain costs low is token budget enforcement. Make sure that you force people to use the right amount of tokens. Sometimes I put a token limit. I only allow maybe 100 input tokens, and I only allow 8,000 output tokens. It all depends what's more important, the input or the output. Sometimes your output can just be a one-word answer, and that's fine. Sometimes your input can be a one-word prompt. That's also fine. It depends on what the task is and what the model is supposed to do. Next, we have observability. The good news about Google Cloud Observability is that we can actually observe different layers, infrastructure metrics, such as computational metrics, large language model behavior metrics, quality metrics, safety metrics, and business KPIs. That's a lot of information. Good news is you can handle this all via Vertex AI. Vertex AI has all these metrics already loaded for you to evaluate and review. So now you're not handling multiple technologies and machines. It's all done in one platform. Then, of course, we have performance testing. So let's assume that we are happy with our model as is. So what we need to do now is test, can it handle a heavy workload? Can it handle traffic spikes? Can it handle several users all at once? Well, we can use load testing to test peak usage and see if we maybe need to give the model more power. We can use benchmarking metrics to test latency, which is the speed of a response. Remember, lower latency is better. We can use chaos engineering, where we literally take away tools, shut them down, and see how the model handles these cases. Does it exit gracefully? We can do quality regression testing, that we test on different versions of the data set and see which version is performing better and see if data quality will impact model performance. We can do cost regression testing, where we can actually lower the average token cost or lower the average token usage and see how that impacts the monthly bill in relation to quality. Then, of course, we can do security penetration testing to see if we can actually find bugs in this. And one of the great things about Google is that it actually does have that prompt injector defender, and it does actually have most commonly used hackable prompts to help us solve the problem. This is actually a very good way of tackling this problem. Now let's discuss how we integrate AI agents into our workflow. Number one, first, we need to think about the 3 horizons: augment, automate, and orchestrate. What is augment? Augment is when it's making human tasks easier to do. What is automate? Where we're creating an autonomous approach or automatic approach of handling these tasks. So no human involvement. Unlike augment, where there's still human involvement, but it's making it easier to do. Then finally, orchestrate, when the model can execute complicated workflows with little to no human involvement. Augment is pretty easy, like using an LLM to research for you. That's augment. Using an LLM to spell check for you. That's augment. Automate's a little bit harder. Using an LLM to create reports, write code, it's a little bit hard. And orchestrate would be the most difficult, because now you're having the LLM essentially perform an entire job role and execute that with very little input from you. So what are some common ways we can integrate these AI agents into our workflow? Well, ideally, we just want to have a native integration. We plug it to our Gmail, Google Doc, or Google Slides. And the good news is Gemini and Gemini agents or Gemini built agents with the agent builder can very easily integrate into most Google products. But if that weren't the case, you have webhook integrations. What we do here is essentially we create an endpoint and then the model communicates with that endpoint to whatever platform we want, Slack, Jira, Salesforce. Another one is that we create an AI wrapper, meaning the model calls the particular tool, the particular API as a tool under a wrapper and then executes commands through that API. Next one could be event driven via PubSub, which is a Google Cloud product for guaranteed message delivery. It can receive the message from PubSub and trigger a response. A common use case of this is traffic sensors. For example, if a traffic sensor detects a crash, the model can immediately trigger a response from emergency medical teams via event-driven messages. Another option is an RPA bridge. What happens if you don't have an API? Not every company has an API. Well, you can use an RPA tool like UPath Automation Anywhere as an agent tool. It basically organizes smaller bots to perform the tasks on user interfaces, so like websites and such, like buy me this product. It can trigger the model to buy the product there, because maybe there's not an API. Another option is to embed the model directly into the application you're using. Can be done through embedded UI widgets. So you know how sometimes you speak to customers and you know that you're like in a smaller chat window speaking to a model? Well, that's would be an example that you embed in a user interface where the model immediately communicates from the AI. And then finally, we have Vertex AI Conversation. Vertex AI Conversation is probably the best way to build a customer service agent that can perform minor tasks. Vertex AI customer service, Vertex AI conversation actually allows us to integrate this into audio customer support, to a certain extent, video customer support, and text customer support. It can be connected to WhatsApp, Google Business Messages. So you can actually create a customer service rep through Dialogflow. They can perform tasks, and the Dialogflow already has maps of solutions that you can do. By this, I mean it can have a map of how to refund you a plane ticket, do a hotel booking, and more. Now, let's talk about how we incorporate these changes. Oftentimes, we need to remember that AI is not a perfect solution. Oftentimes, it comes with some biases. Oftentimes, it takes time to adjust it. I once worked with an organization that preferred using Excel than an AI to give an answer for the simple reason that someone said, I've been using Excel my whole career. So how do we apply this in the workplace? Well, we need to build trust. This is usually done through stakeholder alignment. In stakeholder alignment, we are actually getting skeptics and internal champions to support us. One way to do this is to be transparent. Tell it what the AI does, what are its limits, what it can do. It's very important to talk about the limits because sometimes people don't trust it. And other times people get so excited and then you didn't discuss the limits and then they get disappointed when it doesn't do exactly what they thought it was going to do. Next, which I always recommend, is to do smaller groups of pilots. You get a small group of users to use the artificial intelligence and test how well it works before actually deploying it business wide. Honestly, this is, in my opinion, the best because there is a smaller commitment and everybody can use the tool without having it break at scale. And then that way you can be certain that the tool works correctly before you launch it worldwide. Next, we have skills transition. Often people need to learn how to use artificial intelligence. It's not as easy as we think. So now we create learning programs and skill updates to get people to use AI. Next after this, we have feedback loops. This is where users can report errors that the agent has to improve it. And this can also train artificial intelligence. Then we have governance participation. This is where we get users to set policies, organizations to set policies, and what are the scenarios where we use AI, what are scenarios where we must use AI, and what are scenarios where we don't have to use AI. So what's a good rollout phase strategy? Well, one, you always want to take on an AI project by doing a comprehensive discovery. The discovery should be 2 to 4 weeks long. Find out what are the problems, map the use cases, and assess data readiness and success metrics. Next, you want to think about a proof of concept phase, so that pilot phase. Build the minimum viable product, test, validate, and deploy. Then you want to have your pilot phase where you collect your feedback, iterate and deploy rapidly, fix rapidly assets, and build your safety guardrails. And finally, when it's in a good stage, you scale out to the full user base and integrate it with your systems and build your ML ops pipelines. Now let's talk about ML ops. How do we handle the change of this AI agent? Well, the good news is Vertex AI helps us do this by maintaining version history. Every time you deploy a new version of the model, it will have version control so you can roll back to older versions and the latest version automatically. Google Cloud's Vertex AI has generative AI evaluations that have automated evaluations. So as you deploy a model, it can be immediately evaluated so you can see if it's working as well as you expect it to work. Next, we have A/B testing frameworks. This is where you can test version A of the model and version B and decide which one is better. Vertex AI also has what we call behavioral drift detection. Behavioral drift detection is checking if the model is giving good answers all the time. And if it's not, what is causing it to take a step back and give less than adequate answers? One of the great things about Vertex AI is that it also has the ability to fine tune. This is when you give the model feedback and it improves itself through fine tuning. Fine tuning is when you give the model the feedback and it trains itself on it. Next, you have feature flags. This can be used to enable or disable agent capabilities as you're developing and rolling out new tools. Now let's go to our next section, which is workflow integration. Depending on what solution you're doing, it can be easy or hard. Now, Vertex AI Agent Builder is relatively easy for Google products. For non-Google products like Slack, CRM systems, agents, forms, alerting solutions, it can be a little bit harder. But usually there are ways to integrate this using webhooks and such. So it really will just come down to the scenario that you're in. But as you can see here, we can deploy our agents in email, CRM systems, ERP systems, Jira, and so on and so forth. So you do have the ability to actually deploy these agents even more. So now let's talk about a very important topic, model governance and safety. What is model governance and safety? Model governance is making sure that our model is safe, legally secure, and performs at a high level. Google follows these these 6 principles of artificial intelligence. One, a model should always be accountable for its actions to a human user. So the business owner might be the accountable, the technical owner might be accountable. Next is the model should be transparent in how it makes a decision. 2, the model should be fair and unbiased. Sometimes we have innocent biases that we put in the model due to a training set. So you always need to make sure your model is behaving fair and unbiased. Next, we have privacy, where any personal user data needs to be managed by the model and not outputted. Most companies are GDPR compliant. So private information being leaked out is very serious for a model. Next, we have reliability, making sure the model's answers are accurate, it's secure, and it gives reasonable response times. And then finally, we have human oversight. Human oversight is when we always have a human reviewing the model's performance. So now let's talk about how we achieve these 6 principles. Number 1, we use model safety filters. Google's Gemini models and Vertex AI have built-in safety blockers that look at categories like hate speech, sexual content, and violence. It will not output an answer if it violates one of these categories, and it will not allow an input of an answer if it violates one of these categories. Google Cloud also comes with the Responsible AI Toolkit, which is used to detect any bias in the model and also explain to you if there is a problem with the model. And then it can actually help you debug this. We already talked about grounding, and grounding is essentially when we're checking the answer with a reliable source. Then, of course, we have output validation. Output validation is when the model is actually looking at the answer it gives and determines if it's the correct answer. Then finally, we have action confirmation. Sorry, not finally, but next we have action confirmation, where if it's doing high stake actions like performing financial transactions, account changes, it requires a human to evaluate it before it continues. And finally, we have content moderation. This is where it's checking for outputs, not so much if it's a violation of the safety issue, but more in case there's a policy violation or making sure that the content is relevant to the answer. So those are some of the safety controls that are implemented in Vertex AI. Some of these you can change, some of them you can't, but they are embedded in all solutions inside Vertex AI. Now, remember when you're building a model, Google recommends these principles for responsible AI. Make sure the AI is socially beneficial, avoids unfair bias because bias will happen, be built for safety, be accountable to people, incorporate privacy, and uphold scientific excellence. So these are the principles that you should build your AI solutions with. Now, one of the great things about using artificial intelligence, particularly in the Google space, is that it already comes with understanding of key legal frameworks like the EU AI Act, GDPR, SOC 2, and industry regulations. This ensures that when you do deploy an agent, you can have a certain degree of safety that it will follow these legal documents. And when you're evaluating your model, it does give you reports to check the model evaluation, like user satisfaction, factual accuracy, safety compliance, efficiency, and user calibration. You can control these at any point and also modify them to see which one you feel is more important. So if you think task completion rate is more important, you can actually control it so it behaves more to the task completion rate rather than safety compliance and factual accuracy. However, you should not ignore safety compliance. So why can an agent go wrong? Well, agents will behave unexpectedly. Remember that these agents are primarily meant to always provide an answer, even when they shouldn't, either because they don't have enough information, or it will be the incorrect answer, or it's a dangerous answer. So how do we prepare this? Well, one, we create monitoring alerts to detect problems. Two, if we detect a problem, we immediately need to contain that agent by shutting it down or putting it in a sandbox. Three, we investigate through Google Cloud audit logs, which are automatically deployed to Vertex AI. Four, we remediate, we deploy to a non-production environment, we test, we get sign-off, and we deploy to a production environment. And most importantly, we learn or have the model learn what was this mistake so it can fix it for later. Oftentimes, the biggest problems with the model come through prompt engineering. This is when we give the instructions to the model. Now, we always have to assume that users might give bad instructions. So we need to be thinking in a persona prompt first approach. Give the model a specific role. That role is its goal. Understand the capabilities of that model and make sure that when we do prompt engineering for production, it stays within those capabilities. Make sure it outputs a strict format. Make sure that you add confidence thresholds to the model, saying, don't answer this question unless you have this level of confidence. Make sure that you also summarize long context when we ingest it in system memory from chat history or Redis databases. Because the more tokens we use, the less we can give for an answer. And we want to make sure that it has enough reasoning and thinking time. And always keep different versions of your prompt. Treat them like code, test your prompts, review them, then deploy them. Now, one of the great things about Vertex AI is that it comes with agent design tools to avoid these errors. Vertex AI in the model garden tells you what models are good for what tasks. They actually can output the results in a schema format or in other formats, so you don't have to worry about creating your own custom format. It can actually give you already templatized formats. It actually has the ability to design itself so it doesn't create errors and keeps trying, or exits out gracefully. And it also gives you pretty meaningful error messages inside your solution. So that way it can make it easier for debug. Then we do rate limiting and quotas. This is making sure that your model always has within the limits within its quotas. Making sure that nobody can exceed those limits and give you a large cost to your model. And then, of course, it has the ability to audit any tool it calls. So oftentimes these models will call tools, and we want to make sure that it is calling the tool correctly and there are no potential bugs there. So what's a good practice for data architecture? Well, one is data quality first. This is by far the most important. When you prepare an AI agent, the quality of your data will impact it the most. You've probably heard the saying garbage in, garbage out. Good thing is Vertex AI has data quality checks. Next element is semantic chunking. What do we mean by this? Well, this is when we're going to pass a whole document to the model. Oftentimes, we cannot fit that whole document into the model. So we have to simplify it or summarize it. One of the best ways to give a model instruction is by giving it metadata. Metadata gives us information about the document, the source, the date, the access level, maybe even the usage. Another good practice is data control. Like we said earlier, you want to make sure that models only answer with the data that they are allowed to use. So we can enforce column level and row level security to this. Remember, a model is only as good as the data that you gave it. So if the data is not up to date with the latest one or information, then you need to make sure you maintain data freshness. Vertex AI tells you how often data sets or RAG databases have been updated. And finally, we have synthetic data evaluation. This means that if you don't have the right amount of data to test your model, you give your model a persona, and then it will create synthetic data to test itself based on how people have been testing it. So those are good data architecture practices. Now let's talk about costs. Every model, even in the Gemini family, has a different cost. Usually higher costs give you more performance and larger context windows. The most expensive one would be Gemini Ultra Outputs, which means the type of answer it can give you, followed by Gemini Ultra Input, which is the type of request you're making it in. These two are the premier models, but they obviously cost the most because they can do more complex tasks. And then after that, we have Gemini Pro and Flash. But remember, we've talked about techniques on how to save on cost. If I'm asking what's 1+1, do I really need Gemini Ultra? No, Gemini Flash can handle it. Should I limit the context windows so they don't overload it with tokens? Yes, that keeps cost control. If someone's asking a similar question, can I use caching to solve it? Yes. And can I set up budget alerts? Now, the great thing is Vertex AI already takes care of all the easy set budget alerts. You do have to set up your budget alert yourself, but caching and all other elements are included in there. Now, one of the great things about Vertex AI is that you can move data or your models from other platforms like Azure OpenAI, AWS Bedrock, LangChain Llama Index, or custom to Vertex AI. And it's relatively easy. Remember that Vertex AI already has a model garden, so a lot of already popular models are inside Vertex AI. So all you have to do is just move that knowledge base over and the model over, and it will be fine. And honestly, quite often you don't even have to move the model over because it's already probably in the Vertex AI model garden. Now, let's talk one last time about testing. Remember, you are responsible for your model's behavior, nobody else's. So how do you make sure that your model is being tested accurately? Well, you can use unit testing, integration testing, and end-to-end testing. Unit testing is where we're testing one small element of the model or function. Integration testing is where we're testing it with all the tools in a staging environment. End-to-end testing is where we're testing all steps, even the elements of the model that are touched outside, like a dashboard or the website. Adversarial testing is when we are challenging the model with potential harmful attacks. Load testing is when we're testing the infrastructure. And regression testing is when we run a full evaluation on the suite to see if we're getting the correct answers. So what is coming next? Well, we've already seen multimodal agents, which are agents that can not just generate text, but generate text, images, code, structured data, and more. They're great at understanding the real world context. We're starting to see LLMs being applied in hardware like IoT sensors, robotics, and lab actuators. We're seeing tools like agent-to-agent protocol that's enabling agents from different organizations to collaborate together, such as the Vertex AI agent with an AWS Bedrock agent. And we also see models capable of executing goals over a period of days, weeks, or months. We see models that can self-improve and models that have organizational specific information, such as what we would call sovereign AI. And they're very good at solving tasks related to that organization. Now, what are some common pitfalls that you could have? One is over automating too early. Remember, even though we want to automate, we don't want to always take humans out of the loop. Humans are better at understanding problems than AIs. Then we also want to make sure that we don't skimp out on prompt engineering. Remember, prompt engineering is actually a task done by most users. So we want to have prompt engineering checks to fix this. We also don't want to underinvest in evaluation. Evaluation is key because it will test our model before we deploy it. So often test it with your own prompts. And we don't want to over context the windows, meaning that we don't want to give it too long context windows that it's going to overload it from giving the correct answer. Another one is insufficient data governance. An AI will use all tools that it's capable of using, but sometimes those tools will be too much and give poor answers because it's trying to use everything. And don't forget to use user research. Remember, these tools are going to interact with humans. These AI agents are going to interact with humans. Make sure you use them the way the human intends to use them. So in Vertex AI, we have all these elements that can help us build solid AI solutions. Agent Builder, Agent Engine, Gemini, Pipeline, Workbench, Experiments, and more. So using all these together, we can actually build pretty powerful solutions in the Google Cloud space. So if you want to start building your agent, the first steps is start your foundational work with setting up your Vertex AI project or GCP project, do a tutorial, and identify one high-value use case to try. Second, prototype. Build an agent with 2 or 3 core tools, give it an example data set, then test it. Refine that agent until it gets to a point where you can deploy it in public. And then finally, deploy it as a pilot. Here are all the learning resources that you can use, from practical code labs where you can get hands-on experience, GitHub code examples, official documentation, and skill boost courses. Remember, Agentic AI is a paradigm shift. It is not just here to answer questions, it is built to act as a fully functioning system. You can build all this inside Vertex AI. Remember to build your solutions for trust, not just capability. Start small and build, evaluate constantly, and perform data governance. Any questions, thoughts, or comments so far?
Thank you, Francisco. That was very informative. Now, I know everyone's looking forward to the Q&A session, so go ahead and start putting your questions into the questions panel. And while you do that, I'd like to give the presentation rights over to Ifla, our product marketing person, who's going to introduce you to some of our fantastic promotions and webinar-related courses.
Thank you, Tracy. Insightful session. I believe everyone must have learned something new today or would have been able to brush up their skills around Google Cloud technology.
So firstly, I'm excited to announce that Netcom Learning is now an authorized training partner for Google Cloud, making us your go-to destination for cloud skilling. With this milestone, we are proud to offer comprehensive training across the three leading cloud technologies globally: Microsoft Azure, AWS Cloud, and now Google Cloud. So Netcom Learning, is your one-stop shop for cloud skilling. I would also quickly like to take you through some of our hand picked resources, which we think will immensely help in accelerating your Google Cloud skilling journey. Well, this document here that I'm presenting has been shared with you all in the handout section of GoToWebinar panel. You can download this document and access all the resources and browse all the offerings we have curated for you. So, first up is the list of our recommended courses, which we feel will best suit your learning journey after attending our masterclass. So, all these courses here are hyperlinked. Feel free to go through them post event and check out the course descriptions and prerequisites and the value it can add to you and your team skill sets. Additionally, we have curated a blend of resources, including our upcoming and on demand events, as well as some informative and educational blogs. So you can make the most of these resources to gain extensive knowledge on the Google Cloud topics they cover. Also, here I would like to inform you that today's masterclass session is being recorded. So, in case you want to refer back to any of the topics that were covered by the trainer today, we'll be sharing the recording link with you through emails, and also you can access the link here on the handout so that you can revisit the session and learn at your own pace. Now, apart from our virtual sessions, you can also catch all the relevant updates related to IT and business training on our social media handles. So please feel free to follow us on LinkedIn, Twitter, and Instagram, and also subscribe to our YouTube channel for all the latest updates. Our official pages and channels are linked here on the icons. Finally, if you have any suggestions regarding the topics you would like us to cover in our upcoming webinars and masterclasses, please don't hesitate to send us a direct message or leave a comment on our social media posts, or you can just simply email us at google@netcomlearning.com. We would definitely try to come up with the sessions on your suggested topics. Thank you once again for joining us today. You guys have a good one. Thank you.
Thanks so much for guiding us through that information, Ifla. And now we're going to go ahead and jump right into our question and answer session. First question in the queue is, according to the training materials, what is the primary distinction between traditional AI and agentic AI regarding their core purpose?
So, traditional AI is meant to solve one, maybe two specific tasks. Agentic AI is meant to be very good at generalizing and solving multiple array of tasks. The traditional AI system might only be able to forecast sales, versus an agentic AI system might be able to forecast sales, create reports, and do simulation or modeling, and more. So that would be the two core differences.
Next question. Which component of an AI agent is described as the reasoning engine that interprets goals and decides which tools to invoke?
Yes, that would be the large language model core. That is the one that interprets the tasks and performs the goals.
Next question is, in the context of Vertex AI, which model from the Gemini 2.0 family is recommended for high-volume agent steps and latency-sensitive workflows?
When we're talking about latency sensitivity and high volume step, which is going to perform a lot of actions, the best model, as it is currently, but this could change, would be the Flash model. So the Gemini 2.0 Flash. Just keep in mind that there will be different Flash models coming up. So the number is not so much as important, but the Flash model will generally be the most important.
Next question. The React pattern is the default reasoning loop for Vertex agents. Which of the following best describes the reflex stage of this loop?
Yes. The agent evaluates the action and decides the next step. The reflex stage involves the agent analyzing the outcome of its action and determine if the goal is achieved or does it need to continue. That would be the best way to describe it.
And the last question is, when designing a system prompt for a production-grade agent, why is it critical to include escalation paths?
This is critical because it can define clear conditions where the agent asks for human help rather than guessing. Escalation paths are vital to prevent unpredictable behavior at edge cases or when dealing with sensitive topics.
Once again, I want to remind you that as you leave this session today, you will be presented with a short survey. We would like to request for you to help us by taking a quick moment to participate in that survey. Your feedback really helps us understand your learning experience as we are constantly looking at how we can improve our future sessions. The survey answers are measured on a scale of 1 to 5, 5 representing outstanding and 1 representing poor. We want to thank all of you for joining us today, and if you do come up with any additional questions, feel free to send them to webinar@netcomlearning.com at any time. We hope that you found today's webinar informative, and we look forward to seeing you back here with us soon. Feel free to tell your friends and colleagues about our webinars and other courses. Have a great day, everyone.